I know you've talked about angles in the past, and you've dealt with them a little bit, but it's been a while, and I'm gonna just start from scratch with this. So forgive me if I'm insulting you with the simplicity of some of this stuff, but I really wanna make sure we go from the very beginning and just kind of get back up to speed. First of all, something I wanna just mention is a word. A word that is gonna come up a lot in geometry, and I don't know for sure if you've ever heard it. The word is congruence. Have you talked about congruence in the past? Okay, it's kind of, maybe a little bit. Not a ton, but a little bit maybe, right? Probably last year a little bit, I'm guessing. Okay, so congruence. What does it mean? Congruence is like the noun, and for things to be congruent, what does that mean? Two geometric things are congruent when?
They're exactly the same.
Okay, when they're exactly the same, that's true. Let's be a little more specific. When they have the same what? What is the same? Say it again. Okay, so the same, instead of using the word length, I'm going to say size. Because the size, in some cases, no, you're right. If we're talking about a segment, it would be the length of the segment. But what if it's an angle? Or what if it's a triangle later in life, right? Later this year, we're going to look at congruence of more complex things. We're going to start off with really easy stuff. We'll look at two examples today. But so congruence, there's two things that have to be the same. They have to have same size. That's one thing that has to be true. What's the other thing that has to be true?
Shape.
Same shape. Yeah, they have to have the same shape. Now the top one, the same shape, becomes a lot more important when you're dealing with more complex geometrical things, right? Like triangles or polygons or, even three-dimensionally, polyhedrons, things like that, right? The size is just, is pretty straightforward. When we're talking about things like segments, is the shape thing really all that important? I mean, segments are pretty simple, right? They're just one-dimensional. They can't really have much of a shape, can they? They merely have a length. So for two segments, if I draw this segment and that segment, they have the same shape. They're straight and they're infinitely thin, but are they congruent? No, because they don't have the same size, do they? Right? So really the only part we have to worry about is the size of the segment, meaning its length. Sure. Its length, or another way we could even think of it is the distance between its endpoints, right? So two segments are congruent if what? If they same shape and same size, but the shape's guaranteed because they're segments. So what's really the only thing that has to be true for segments? Lengths have to be the same, right? Two segments are congruent if their lengths are equal. So there's another point I want to make about this. Whenever we talk about measurements, we talk about measurements being equal because measurements can always be expressed as numbers, right? The length of a segment is a specific number, right? We find it using the distance formula. Okay, so measurements are equal, but geometric things are not equal. They're congruent, right? So we'd say the segments are congruent, but their lengths are equal. See the difference? Okay? So we'll come back to that idea of congruence and what it means to be congruent. Let's go back and review angles for a second. So an angle just consists of two different rays that have the same initial point, right? They're both emanating from the same point. So in this case, we get this angle because we get, what's one of those two rays called? How would you name one of those two rays? Ray AC. Okay, so we got ray AC and ray AB. And if you combine those two rays, because they're both starting at point A, they form an angle, right? That's it. What is the anatomy of an angle? Well, angles have a vertex, which is the initial point of both rays, and then they have sides. So this, one of the sides is ray AC and the other side is ray AB. That's it. There's not much to them, okay? How do we name angles? So we've got this angle up here. What are some different ways, don't say it out loud, what are some different ways we could name this angle? Do we have an idea? Give me one legit name for this. Yes? Okay, it is acute, you're right. That's how we could classify it. How could we name this specific angle? Elton, what's one way?
Angle CAB.
Okay, one way we could do this is to say angle, and that's our symbol for angle, by the way, right? Angle CAD. That's correct. We'll come back and talk about why. What's another one? Oh, what's CAB? Sorry. No, that means angle, okay? That's one way. What's another way? Somebody have another idea? Yes. We could just call it angle A, sure. Okay, what else? What do you think? Yes, sir. Angle BAC. Okay, what about, I'm going to throw one out. You tell me if this is good or not. What about angle ABC? No. How come? Ah, okay, that one's no good. Yeah, that one's no good because look at the pattern of these angles that were correct. We had to start with a point on, doesn't matter which side, but one of the two sides, we have to go through the vertex to the other side. So when you're naming an angle with 3 points, the vertex always has to be the middle point, right? Think of it as giving an ant directions as to how to walk along the angle. He has to go from point C to point A to point B, or he can go backwards from B to A to C. Now, what about this one right here? That's fine. That's fine. Talk to me about that. What do you think about naming an angle that way? It's fine this time, but can you ever think of a case where maybe it wouldn't be okay? What do you think? Emma, you got an idea?
If there are like other ways coming off it.
Yeah. What if you had something like, for example, like that? Could I label any of those angles? Can everybody see? I'll make that bigger. You can see that better. Could I name any of those angles angle Q? No, I couldn't, because that wouldn't be specific enough, would it? Right? Angle Q could refer to any of those then, right? So that's a case where because there are multiple angles kind of being jumbled up in one, we've got to be very specific and by the book and use the 3-point method for naming the angle. Okay? Questions? Okay. All right. So moving on. Okay, we all know that we measure angles with a protractor, right? Old school. Have you all used a protractor?
Yeah.
Okay, so I mean this is something that's sort of going away more and more because we don't use this kind of stuff as much anymore now in the digital age. But all you do with the protractor, just in case you haven't ever done this, there's a little hole down here at the base. You put the vertex of the angle in that little hole, which lines up with these two X and Y axes essentially, right? And then you're going to line up one side of the angle with 0, either on this side or on this side. It'd be fine. Notice that the angle measures using the bottom set of numbers. It starts at 0 and opens up towards 90 and eventually 180. So you can orient the angle to the right, or if you start on this side, you just use the outside measures, right? And they start at 0 and open up to 90 and off to 180. And no big deal. What we'll be doing instead, have you ever used a program called Geometer Sketchpad? You haven't? Okay, it's fun. You're going to like it. We're going to use, we'll use instead of doing kind of paper and pencil constructions, we're going to do constructions on a computer using a geometry software program. Either that one, which we have here at school, or there's even another one that you can download for free at home called, I can't think of it off the top of my head, but I've got it, and it's just as good. Honestly, it's just as good. So there's another one you can also use outside of school if you want to. At school, which is where we'll do most of this anyways in the computer lab, we'll use Sketchpad. We're not quite there yet, but you'll really like it. It really is fun to use. You can do some pretty cool stuff with it. I'll go through some tutorials and show you how, and then I'll even have you do some stuff with Sketchpad where I might even have you, I mean, you can do some kind of fun stuff, some design stuff where you could design like a pendulum, or you can be creative with it too. Using geometry, you can create some kind of cool stuff. You'll see when we get there, but I promise you'll like it. If we measure two angles here, let's say we measure with a protractor this angle VAC or CAV, whatever you want to call it. What is that protractor telling us the measure of that angle is? 50 degrees, right? Okay, we've got another angle down here, angle DEF or FED. What is that one? What is its measure? And how do you know? Because it says 50 degrees where the angle sits, right? So that's our way of showing in a drawing, and you're all familiar with that this angle has a measure of 50 degrees. Okay, I want you to do something. I want you to think about something for a second. I want you to, and this, we'll talk more. I'm going to see you guys a lot over the next few years. So we're going to have this discussion again and again and again. And hopefully we'll have it eventually. We'll be having it in physics and calculus, all kinds of other classes. But the world is divided up into, really there's two kinds of motion if we want to think about it in terms of physics, or if we want to think about it in terms of measuring. I don't want to say this. If I want to think about it in terms of measuring relative positions of objects, we can do this in a number of ways. You can kind of think of the world as being broken up into linear land and like Angulvania. And they do similar things, but just in slightly different ways. In linear land, that's where we're going to measure everything in terms of straight distances, right? So for example, if I want to walk from here to here, well, the path I've just walked could be modeled by a line segment, right? And it's going to have a length which corresponds to how far I walked, right? Now I could also do stuff like this though. I could spin around and I haven't moved at all, right? From my position. My feet have, I've stayed essentially right over the same spot on the floor, agreed? Did I move though? I did. It took some energy for me to do that. And so I don't know how the energy comparison would be. I don't know which one required more energy, spinning around or walking here, but they were both movements, right? Would you agree that this is a very different kind of movement? Okay, this is an angular movement and that's a linear movement, right? We need to be able to describe both of those. If I'm talking to somebody over here and I pivot to talk to somebody over here, well, I pivoted through some angle, didn't I? I'm looking straight ahead here, now I'm looking straight ahead there, right? So do you see that you can kind of make some kind of a connection there? And this is going to seem a little strange now, but it'll get clearer and this connection will grow stronger as we go through the class and as you kind of think more and more about this. About the most basic thing I can do if I want to do something in linear land is just walk from point A to point B, which corresponds to about the simplest geometric thing that I can, other than a point, that I can have in linear land, which is a line segment, right? Completely described by the distance. How far did I walk? In Angulvania, about the simplest thing I can do is just rotate a little bit, right? I rotated from here to here through an angle. Those are sort of equivalent to each other, aren't they? The easiest thing of just walking from point A to point B, which corresponds to a segment in linear land, is like the simplest piece of Angulvania, which is an angle, right? Make sense? This happens a lot. Just to kind of give you some incentive for going further with this, I'm going to pose a little problem for you here. What would happen, okay, let's say I took 2 cans of pop and I lined them up at the top of a long incline. They're next to each other, but the incline is carved into, let's say it's got 2 different kinds of materials. On the left, on my left, so you're right, let's say it's a really slippery surface. It's highly polished. Maybe we we rubbed it with wax paper or something that's really slippery. On the right side, it's kind of rough, something sort of like sandpaper, right? If I put these two cans, imagine I've got two of them, if I sit them up side by side and let them go, what are you going to observe, do you think? What do you think is going to happen? What's going to happen to the can of pop that I sit on the incline that's really slippery? It's maybe hit the bottom first. Describe its motion.
It's gonna more slide down.
Okay, it might slide a little bit, right? It might slide a little bit, and whereas the other one, if it's sort of a rougher surface, what's it gonna do?
It's gonna roll.
Okay, it's maybe not gonna slide at all, but what's it gonna do? It's gonna roll. We get different kinds of motion. Which one's gonna go faster initially? Probably the one that's sliding, right? Agreed? Okay. Which one is going to maybe generate the most heat as it's moving?
Rolling.
Oh, I could see both ways on this one. When things, rub your hands together, do this for a second. What do you notice? Oh, they get a little warm, don't they? You got friction, right? There's a little friction there. And friction typically is something that we get when objects slide by each other, right? So maybe the can that's sliding down, if you measured it very carefully at the end, might be a little warmer than the other can, possibly, right? I'm just throwing this stuff out there. Okay, when we get to the bottom then, let's just say that when they get to the bottom, they hit this level plateau and they just start moving, right? Which one do you think is probably going to go further in the long run? The rolling one might, yeah. There's a lot of stuff, I mean, that seems like at first you're probably thinking, wow, what kind of, but there's a lot to explore there, isn't there? There's a lot of stuff that might be interesting to figure out how it really happened. Why is it so different, and why can we speculate about this stuff? Simply because one of the cans is rolling and the other one is not, right? So in physics, there's a huge difference between, rotational motion and linear motion. But rotational motion is a really important thing. We just don't think about it as much. In your car, there's something called a flywheel in your car that has to turn real fast to keep the engine to keep it running smoothly. Without that, your car wouldn't run. Right? There's a lot of this stuff that goes on that you never think about that's really important. In order to be able to explore any of that stuff, you have to understand Anglemania. You have to understand how, the geometry of angles and rotation, and this is where it all starts, right? So I'm just throwing that out there as a reason for why is this important. That's one big reason. We could never know. I mean, you're going to want to know someday what's going to happen to those pop cans. You're never going to be able to know if you don't know about angles. Yes, sir.
How would you classify non-linear movement like a parabola?
Well, it's a little more complicated, but yeah, it's going to involve a little bit of both, right? I'm not going to spend a lot of time on that, but it's a really good question. I got to, in a class like this, I got to be able to take time every once in a while and answer good questions. So if I understand your question, I think this is going to be a good answer. You tell me if it's not. So if we think about something like, let's say here's our sun, for example. There's our sun, and here's the Earth. Does the Earth travel in a perfectly circular orbit around the sun? No, it's a little bit elliptical, isn't it? Right, slightly elliptical. So I'm going to exaggerate it. It's going to go kind of like that a little bit. It's almost a circle. What about something like a comet? A comet is also, they orbit in something called the Oort cloud, which is on the kind of the edge of our solar system. That's where they are most of the time. But they orbit our sun. You guys you've seen pictures of comets, and I don't know if you've ever seen a comet, but you've seen pictures of comets. Their orbit is much, much more eccentric. Their orbit would look more like, like this. So it's really highly elliptical, kind of orbit that is. The question is, say your question one more time.
I said, how would you classify that? I was specifically talking about a parabola, like a semicircle maybe.
Okay, like a parabola. Parabola would be if there were some extra solar rock or something that came in like this and was deflected but never made its way back. Same kind of a thing. You can do it the same way. You can still talk about the angle that this thing is traveling through. Let's take this example over here. Let's say the Earth between these months, it's still going to travel through a given angle. And that is important. That's related to how fast it's going. It's related to lots of interesting stuff. For example, you know that when we study physics, hopefully you'll all be studying physics later, that the area that is traveled through, like if I think of the area of this arc right here for the planet as it travels around the sun, that area is being swept out at a constant rate. And so when it's very far away out here, the angle can be a little bit smaller because it's a longer sector, right? So when it travels through just a little bit, it gets quite a bit of area because it's so far away. But when it's going by the sun, would you agree that it's going to have to go, in order to get that much area, it's going to have to travel further through a bigger angle? You kind of see that? So these are just more examples of angles. I mean, this is all the stuff that we're starting to talk about now. To understand it later on, you know, we got to have a good understanding of the geometry because this is very geometric stuff. Okay? All right, I'm going to leave it at that. We'll probably come back to that stuff sometimes. It's fun to talk about. But let's push on through a little bit of the geometry that we need to know to get there. So, congruent angles then. What do you suppose is true for angles? If we made this comparison, we said that segments, really simple small pieces of linear land, are congruent just if their lengths are the same. How do you suppose angles are congruent? Don't angles all pretty much look the same, right? They all consist of the same stuff. They all have two sides and a vertex, right? How could, and they go forever, right? So how could two angles be congruent? What do you think? Okay, they have to have the same amount of degrees. Now the way we would say that in geometry is they'd have to have the same measure, okay? So, for example, these two angles right here are congruent because they both have measures of 50 degrees, okay? So just like for segments, all it takes is compare the lengths. For angles, all you have to do is compare the measures of the angles, okay? If the measures are equal, then the angles are congruent. All right, so one other thing we can say about angles is that, does it make sense that if we're talking about this angle with a vertex of A, this acute angle, this is the interior, because it's the part that's trapped between the two rays, and everything else out here is the exterior, okay? Just like we said yesterday, we talked about the segment addition postulate. Remember we said something about, and I want you to see that, are you starting to see how there's a direct comparison here? Everything we did yesterday with, you know, with segments, we're just doing today with angles, right? Same idea. We said yesterday if we had points A, B, and C with some point in between, right? What did we say about those segments? Yeah, what can we say about the length of segment AC? So length AC, length BC, or CB let's call it, and length AB. What has to be true? Yeah, AC plus CB equals AB, right? Because C is on the interior, right? It's between A and B. Make sense? Okay? Does it surprise you that the same thing is true for angles? If we have two, what we would call adjacent angles, two angles that share one side, like in this case we've got angles R, S, P, right? And we've got angle P, S, T. What do you think the measures of those angles, how are they going to relate to the big angle R, S, T? Same way, right? Same way. Because this side SP is on the interior of the big angle, then the same principle holds. The sum of the, or excuse me, the measure of the blue angle plus the measure of the red angle equals the measure of the green angle. Okay, make sense? All right, so solve that for me, please. Okay, so let's see if we can get, we gotta be able to set up some kind of an equation here, right? If we're trying to solve this for x, we're gonna do this a lot in geometry. We wanna use some geometry relationship to be able to set up an algebra equation that we can solve. So, Gabe, help us out here. What can you tell us about this that might help us set up an equation? Okay, the whole thing has to equal 84. Good, right? So that's important. So, Duncan, how can I take that and run with it? How could I maybe set up an equation then?
X, or 84 equals 2x plus 3.
Okay, so 2x plus 3 equals 84? Does that seem right?
Well, it's 3x plus 3.
Oh, 3x. Ah, okay. So it's 2x plus 3 plus x. I got you.
Okay.
Plus x equals 84. Does that seem better?
Yes.
That seems better, doesn't it? Because 2x plus 3 is the measure of this bottom angle, right, by itself. X is the measure of the top angle by itself. 84 is the measure of the whole thing. And because they're adjacent angles, we know that the sums of those two little angles must equal the measure of the big angle, right? Okay, so what do we get if we do that then? 3x plus 3 equals 84. So what do I do? Subtract 3, divide by 3, and what do I get? X equals 27? I think 27, because I'm going to get 81 divided by 3. So 27.
Yeah.
Okay. How could I check it? Plug it in, make sure it works, make sure it gives me back everything I needed to give me back, right? That adds up to 84. Okay? All right. That's pretty good. You're thinking you're pretty smart. Try that one. Okay, so we're going to run out of time, so maybe let's come together here and talk about this. Any ideas? What's that?
22.
What'd you get? 8?
Yes.
You're right. You're right.
Wow,
It's
that's
8.
so cool.
Okay, but how'd you get that?
Yes,
Guess and check. Okay. I figured that. And that's fine. 8 works this time. But what if the answer had been like something that you couldn't guess and check? Like a decimal or an irrational number or something like that.
Give up.
So no, that's not the right answer. Absolutely not. So how could we be, and this is what we want as mathematicians, we want to be able to figure out how could we go about this systematically, which means algebraically for us. First of all, can we set up an equation? That's the main thing. If we can set up an equation, then we can, as I like to say, we can kind of shift into algebra mode. And we'll do that a lot. Geometry mode is where we have to understand the relationships well enough to set up an algebraic equation, but then oftentimes once we get that equation, we can just focus in and be algebraic, right? So what do you think? What's an equation that we could begin with here?
Squared plus 3x minus 34 equals.
Okay, so we got x squared, we got maybe the sum of these two angles equals this, right?
Yeah.
So x squared minus 34, and you have a good idea. It's a really good idea, Daphne. I'll do that in a second. So x squared minus 34 plus 3x equals 54. Now we want to write these, and this is stuff that you haven't really done that much of, but we want to write these as we'll talk a lot more about, this year a little bit, next year a lot, we'll want to write these in descending order of power. We want to organize it. So the x squareds, then the x's, then the constants. So good suggestion. Let's rewrite this as x squared plus 3x minus 34 equals 54. Okay, there's an equation. Now we're in algebra mode. We can just forget about the geometry aspect of this completely for now. What next? Any ideas? What do you think, Alex?
Add 34.
Okay, I can see where that's a real common thing to do here would be to add 34 because in the past we've always tried to isolate x, right? Okay, there's a problem here though. And this goes back to something we talked about just a little bit at the beginning of the year. We actually did one example, sort of like this. We've got a problem here that's different than the kinds of problems you faced in the past. We've got x squareds and x's, and those are not like terms, and so they can't be combined. Remember that as we go back, when we went through our algebra review at the beginning, when we were solving for variables, I always said that if you can point to a single variable, then you can always isolate it. But can I do that here? I can't. I'm always going to be pointing at two different x's because they don't combine, right? So it's a different approach. It's a different approach. What we're going to do here instead, and this is, don't panic. This is stuff, this is like Algebra 2 stuff, but we're going to do a little bit of this year. What we want to do instead is put this into what we call standard form and set it equal to 0. Okay, so we're going to subtract 54 from both sides.
I put so much more effort into it than it's not needed to.
And what do we get if we do that? On this side, we get x squared plus 3x minus 88 equals 0. Okay, now, there's a reason we did this. Remember when I had you guys do that warm-up, when I had you multiply those ridiculous numbers, but then everyone knew the answer in the end was 0. How come? Because I multiplied by 0, right? Because that's a unique property at 0. The only way you can multiply things and get 0 is when you multiply by 0 itself, right? So if we were able to, this is a pretty complicated function to try to come to coax a solution out of, because the x's show up in so many places. Duncan did it by trial and error, essentially, by guess and check. But that won't work always, will it? If we can, though, if we're able to take this quadratic factor and break it up into, factor it, right? Break it up into smaller pieces, the product of those pieces could only be 0 when either one of those small pieces is 0, right? This is what we call the zero product property. Does that factor?
Yeah.
Can you think of two numbers that multiply to negative 88 and add the positive 3?
11 times 8.
Oh, okay, so we're going to get positive 11 and negative 8. Good. Everybody agree? Okay. So plus 11 minus 8. That's huge that we're able to do that. Because now that we've got this broken into small pieces, when could the product of those two factors equal 0? What's one case where it could equal 0? Okay. Go say it again. It was multiplied by 0. So either one of two things has to happen for this product to equal 0. Either x plus 11, that factor, has to equal 0, or this factor, x minus 8, has to equal 0. Those are pretty easy equations to solve. When is this first equation equal to 0? When x equals? How about this one? Positive 8. Okay, so the math gods in their infinite wisdom gave us back two solutions here. There is mathematical significance to both of those solutions, but now we got to shift back into geometry mode. And we have to see, do they both make sense in our original problem, in the context of the problem? So if we scoot back up here, our two solutions were, oh my gosh, you got to be kidding me. Just when I was getting exciting. Okay, we'll go to the lab. We'll take 2 minutes to finish this up, and then we'll go to the lab tomorrow. Check your homework. I'll have homework up this afternoon.